In our last two examples, we want to look at solving systems of 4 linear inequality statements. Obviously, these problems are going to be a little bit different because we have additional statements to consider. In this case, our first two are x greater than or equal to 0 and y greater than or equal to 0. To start things off, what we can do is graph the lines x equals 0 and y equals 0. Since those first two statements tell us that x and y both have to be positive, that tells us that whatever our solution is, our final shaded region, is going to be restricted to the first quadrant. We won't shade anything in quadrants 2, 3, or 4. We can apply the processes that we applied in our previous examples to the last two inequality statements, rewriting inequality 1 as y equals negative x plus 2, and rewriting inequality 2 as y equals negative 5x plus 10. Graphing equation 2, we have an intercept at 10 and a slope of negative 5 over 1. Graphing equation 2, we have an intercept at 2 and a slope of negative 1. And now we have each of our 4 lines that create our boundaries set up, and we need to look at test points. In this case, if we consider the point 3, 1, that xy pair would be a solution for all 4 inequality statements, which we could check through substitution. So what that tells us is we would shade this region of our graph, keeping in mind we're not shading any portion of the graph outside the first quadrant due to those boundaries of x equals 0 and y equals 0. So our shaded region has this boundary, this sort of, well, they're all geometric shapes, but the shape bounded by x equals 0, that line corresponding to inequality 2, and y equals 0. Beyond just constructing that graph, we can go on to say that this is an unbounded region. Since the shaded area continues in all directions here into the first quadrant, so even though we don't represent that all, we assume that that region is continuing to go on. And we can also identify what we refer to as the corner points. So any of the points along the boundary where our bounded region sort of changes direction. In this case, we have one at 0, 10, because again, this bounded region changes direction, takes a sort of short turn there. So we have a corner point at 0, 10, and another one at 2, 0. Because again, as we follow this bounded line, this line bounding our region, we take a short turn, that bounded area sort of changes directions, giving us a second corner point. In example 8, we have a nearly identical problem, but what's happened is the direction of the inequality statements for these last two statements have flipped directions. This means we'll still have the boundary line x equals 0, and y equals 0. We'll end up with our line that had an intercept at 10 and at 2, or I should say at 0, 10, and 2, 0. and our other line that had a y-intercept at 2 and an x-intercept at 2. And what we would find now, since the direction of those inequality statements changed for 2 of those statements, is that it would be this small triangular region that we would want to shade to represent all of our solutions. As a test point, we could use 1, 1/2, which would be contained in this bounded triangular region. And that coordinate pair would satisfy all 4 inequality statements, giving us, in this case, a bounded region for our solution. And corner points at 0, 0, 0, 2, and 2, 0, where each of those 3 points represent the corners of this bounded region.